So now, after seeing the basic viscosity behavior, like rheology behavior for different types of slurry, liquid, or suspension, let's look at the actual examples on viscosity. We are looking at silicon dioxide. Silicon dioxide IEP 3.7, which means when pH is roughly this value, we have very little charge, the particles tend to agglomerate. And then this is last time we mentioned the zeta potential versus pH 3.7. So when I'm very close to 4, my zeta potential is close to 0 because that's essentially 0 net charge around the particle surface. And then when I have a higher and higher pH, the solution become more and more basic, have more hydroxy group negatively charged, my zeta potential become negative. And then when I'm around here, I have a lot of negative charge on the particles are stable. Okay, they do not come together easily, do not agglomerate. And this is the measured viscosity versus shear rate or shearing strain rate, 1/second, unit 1/second. This is viscosity. Okay. So let's first see viscosity behavior clearly changes with pH. Viscosity behavior will change with pH from this plot. Where pH 4, pH 6 to 9, pH 10. Okay. And then let's first see when our viscosity around 4, where on this plot? Roughly here, right? Viscosity is, pH is 4 means, okay, very little charge. The particles agglomerate, and then because the particles agglomerate, they become larger, and they interfere with each other, so which means at the low shearing strain rate, I have high viscosity. On the other hand, it shows shear thinning behavior, shear thinning, which means when I try to shear it more, when I try to shear at higher strain rate, thinning means viscosity drops. Because although the particles are kind of agglomerate, but they're not strongly bonded together, when you really try to shave them, they kind of separate. They kind of fall back to the behavior like you are intrinsic liquid, like water, low viscosity. Of course, this is for 30 volume percent of solid. Okay. On the other hand, when we have relatively higher pH, around 6 to 9, 6 to 9, 6 to 9, we're kind of in this behavior. We said, okay, when we're 6 to 9, we have relatively high zeta potential. The particles have a lot of charge on the surface, meaning electrostatic stabilization. The particles are well stabilized. They do not agglomerate. And then what people observed is this slurry or suspension behave like a so-called Newtonian fluid. The viscosity does not really change as we change the shearing strain rate. That dispersed pretty well, and you essentially are measuring the viscosity of the water essentially. Okay, it doesn't really change with strain rate. And finally, when we increase the pH to beyond 10, to go to too high. And remember we said, okay, when there's too much electrolyte within the suspension, too high so-called, read to yourself, ionic strength, too much electrolyte, what effective they are going to do is to compress the double layer or so-called reduce the valence. Compress, which means the particles are not that further apart. Okay, they're getting closer and the friction become higher, and as a result, the suspension starts to agglomerate slightly again, And that's what people observed. When the particles start to agglomerate again, the viscosity, as compared to well dispersed, become slightly higher again, and showing a weak shear thinning behavior. Okay? Let's look at another example, related. We are looking at aluminum oxide, IEP 829, which means zeta potential at around near middle. 8 to 9, I have 0 zeta potential, little charge. Low pH, I have more positive zeta potential. High pH, more negative zeta potential. Okay? And then people measured viscosity. Viscosity versus pH, assuming he's measuring under a constant shearing strain rate. But essentially, what do we get? What we get is when pH is in the, around in the middle, 7 to 10, from low zeta potential, the particles agglomerate, severe agglomeration, the viscosity is high viscosity, and of course, they also should display the so-called shear thinning behavior. On the other hand, when we get to decrease from 7 or increase further from 10, I start to develop either positive charge or negative charge, electrostatic stabilization, and then they lead to stable suspension and relatively low viscosity. You are again measuring the viscosity behavior of water again. And finally, when you get to too low pH or too high pH, too low pH, too high pH, on either side, you are having too high concentration of electrolyte, which essentially so-called too high ionic strength, compressed, double layer, smaller the balance, and agglomeration, slight agglomeration again, and viscosity starts to increase again. Okay?